for H6Cl2, you need to calculate the degree of unsaturation first. Yeah, so first step, calculate the degree of unsaturation. Yeah, so we said you treat any halogen as hydrogens. So C4H6Cl2 is exactly the same as C4H8. Okay. And then we compare it with fully saturated hydrocarbon. So for saturated hydrocarbon, the formula is CnH2n plus 2. Yeah. So compare with C4H8, it should be C4H10. So you see you lose 2 hydrogens, the degree of unsaturation is 1. Okay. Yeah. So degree of unsaturation equals to 1. There's 2 possibilities. Yeah, can everyone type it to the Skype chat? If degree of unsaturation equals to 1, what this could be? Yeah, it's either a double bond or a ring. Okay, it's either a double bond or a ring. And then we know halogens and hydrogens, they never form double bond. So this double bond could only be CC double bond, okay, because halogen never form double bond. Okay, yeah. So we start with 2 different type of functional group isomers, and then you're just going to start with chain branch isomer. Okay, yeah. So start with functional group isomer. Yeah, we know the functional group isomer could be a double bond or could be a ring. Okay, and then we're just going to consider all the chain and branch isomer first. Okay. Yeah. So with double bond and then 4 carbons. Okay, with double bond and 4 carbons, the only possibility is 4 in a straight chain. And then with double bond in the first position, second position, the third position would be the same as the first. Okay, yeah. So they could be a straight chain, or they could be in different branch. Okay, yeah, or they could be in different branch. So that's 3 different versions for double bond. It can't be anything else. Okay, and then you just need to think about the rings. Okay, so you can have a 4-membered ring. Okay, yeah. And then or you can have a 3-membered ring with a methyl group. You can't have a 2-membered ring. Okay, yeah. So all the isomers would be based on these 5 different type. And then based on this 5 different type, what you need to do is now replace 2 hydrogen by 2 chlorine. Yeah, consider all the positional isomers. Yeah, so if we consider the chain and branch isomers, it would be 5. Okay, yeah, functional group isomer, there's 2. And now let's consider all the positional isomer. If you consider all the positional isomers, yeah, I think in the end you will get 23. Okay. There are 23 positional isomers. And then on top of that, we can consider all the cis and trans isomers, which is geometric isomer. Yeah, and then overall answer is 36. Yeah, so for this molecule here, C4H6Cl2, overall there are 36 isomers. Yeah. So let's start with these 5 and then trying to draw them one by one so we don't miss anything. Yeah, so basically we just have a big table with these 5 things. So this one, this one, this one, this one, and this one. Yeah, so we'll just be looking at these 5 things. Yeah, and then we're just going to draw all the potential isomers. Okay. Yeah. So all you need to do now is just replace 2Cl by 2 hydrogen. Okay. Yeah, so replace 2 hydrogen by the 2 chlorine atom. So you can have, so remember, because there are 2 chlorine, yeah, so there are 2 different cases. Case 1 is 2 chlorine on the same carbon. And then case 2 is 2 chloro on different carbon. Yeah, so let's start drawing them. Let's consider first of all the 2 chloro atoms are on the same carbon. Okay, yeah, so they can be on the same carbon. Yeah, they could both on the first carbon, and then they could both on the second carbon. That's impossible. Okay, they can't be both on the second carbon because the second carbon already have 3 bonds. However, they could both on the third carbon. That's fine. And then they could both on the fourth carbon. That's also fine. And then I don't think you can come up with anything else. Okay. The reason they can't both on the second carbon because the second carbon already have 3 bonds. Yeah. So now that's chloro on the same carbon. Now let's consider the cases where the chloros are on different carbons. Okay. Yeah. So the chlorine atoms can be in the 1, 2 position. They can be in 1, 3 position, and then they can be in 1, 4 position. And then they could also in 2, 4 position, and they can be in 3, 4 position. Yeah. So just note, if it is a single bond, then this 1, 2, and 3, 4 position would be exactly the same. However, it is double bond, so you lost that symmetry in the middle. Yeah, so the first compound and then the last compound here is different. Okay, so you have 1, 2, 1, 3, 2, 1, 2, 1, 3, 1, 4, 2, 4, and 3, 4. Okay, and I don't think we can have anything. Oh, sorry, yeah, we can also have 2, 3. Oops. Yeah, so I have 2, 3, 2, 4, and 3, 4. Yeah. So those are all the positional isomers with the first one. Okay. Yeah. If everyone happy with this, could you please type a 1 to the Skype chat? Yeah, so there are 9 in total. Okay. Yeah, so now let's have a look at the next one with this. Okay. Yeah, so again, we can have 2 chlorines on the same carbon. Yeah, and they can't really be on the second carbon or the third carbon because they already have 3 bonds. They can't be in the fourth carbon because it would be the same as the first carbon. So that's all the cases when the 2 chloros on the same carbon. Okay, and then you just need to consider what if the 2 chloro are on different carbon. Okay, yeah, so there will be the 2 chloro would be in different carbon. You can have 1, 2. Okay, and then you can have 1, 3, and you can have 1, 4. Okay, yeah, so 1, 2, 1, 3, 1, 4, they're all different, and then just 2, 3. Okay. Yeah, because 2, 4, it would be the same as 1, 3, so there's only 5 in total. I don't think you can come up with anything else. Yeah. Yeah, so that's the 5 isomers for that. If everyone happy with this, could you please type a 1 to the Skype chat? If anything you don't understand, please make sure you ask. Okay, so now let's consider the last one. Okay, yeah. So the last one, first of all, we can have 2 chloro on the same carbon. If you want 2 chloro on the same carbon, we can have this. Okay, so they're both over here, or we can have they both attached to the end. Okay, yeah. So whether the 2 chloro atoms attached to this carbon or that carbon, those 2 carbons are exactly the same. Okay, those 2 carbons are exactly the same. Oh, sorry, that should be a carbon, not a chlorine. Yeah, and then this compound. Yeah, so because you can draw it like this, so you can see these 2 carbons are the same. And then the middle carbon is already full of 4 bonds, so you can't put anything there. And then, yeah, so there's only 2 situations if you put the 2 chloros on the same carbon. Yeah, and then you can also put the 2 chloros on different carbons. So remember, you can't really put it in the middle. Yeah, so we can put one here and one over there. So that's one situation. And then you can put both at the end. Okay. Yeah, both at the end. Yeah, so that's 4 possibilities. So 2 of them is 2 on the same carbon, 2 of them is 2 on different carbons. And yeah, I don't think you can come up with anything else. Yeah, so that's 4 isomers for this. Okay. Yeah, now let's just have a look at this squared one. So again, okay, we can put the 2 chlorine on the same carbon. But in this case, yeah, it doesn't matter which position you put, they're all exactly the same. Okay, those 4 positions are identical. So you can only come up with one structure if you put all of them on the same carbon. Or you can put them on different carbons. Yeah, so you can put them into 1, 2 position, or you can put them into 1, 3 position. But that's it. You can't put them into 1, 4 position because 1, 4 position would be the same as 1, 2 position. Yeah, so those are the only 3 isomers. Okay, and then the last one. Yeah, the last one. First of all, we can put the 2 chlorine on the same carbon. Yeah, so you can put it here. You can't put it at this position there because that's already 3 bond. And we can put it on either base of the triangle. Yeah, so you can put the 2 chlorine over there. So that's the only 2 situations where we put the 2 chloro on the same carbon. Yeah, because if you put the chlorine, 2 of them here, or 2 of them over the other corner, these are equivalent, okay? It doesn't have any difference. Yeah. So that's all the situations when you put 2 chloro on the same carbon. And then we can put the 2 chlorine on different carbon. Okay. Yeah, so now when we put the 2 chlorine on different carbon, we can put one in the middle, yeah, and then put one on the top. Yeah, put one in the middle and then put one down the side. Yeah, yeah. So down the left side or down the right side, it would be the same. Yeah. So we consider all the cases with middle. Now let's go to the side. Yeah. So you can have 2 chloro on the side. or you can have one chloro on the side, one chloro on the top. Yeah, I think that's it. I don't think we can find anything else. Okay, so this one we have 1, 2, 3, 4, 5, 6. 6 different possibilities. Yeah, so that's all the positional isomer. Okay, all the positional isomer. Yeah. So the next stage, we just need to look at one or each of these, whether they have geometric isomer. So geometric isomer is actually the easiest. Okay, it's actually the easiest. So if you have a double bond, and then one side of the double bond, okay, one side of the double bond, if you have the same thing, and then this molecule have no geometric isomer. Okay, this molecule have no geometric isomer. And then if you have this x1 and x2, and then y1 and y2, okay. Yeah. So you only care about each side of the double bond. If x1 doesn't equals to x2, and if y1 doesn't equals to y2, it's 300%. There's definitely a geometric isomer. Okay, there's 300% definitely a geometric isomer. And then one of them would be cis, one of them would be trans, or one of them would be E, one of them would be Z. Yeah, so let's just quickly go through the first, so let's just go through the first 9 isomers. Okay, so first of all, you see there's a symmetrical, so you can see on the same side of the double bond, the two things are exactly the same. So this one has no geometric isomer. Okay, this one here, there are 2 hydrogens, so this one definitely no geometric isomer. This one here, there are 2 hydrogens, so there's definitely no geometric isomer. Yeah. So the next one you can see, this is a hydrogen, this is a chlorine. This is a hydrogen, this is a hydrogen, this is a chlorine, and then the other side is a chlorine and the acyl group. So this one definitely have an E and Z isomer. Okay? This one definitely have an E and Z isomer. Yeah, the next one you can see the 2 groups are different, so that one definitely have a E and Z isomer. Yeah, and then this one, the 2 sides are different, so it's definitely have an E and Z isomer. Yeah, this one you can see 2 hydrogen on this carbon, so there's definitely no geometric isomer. This one, 2 hydrogen on the same side of the carbon-carbon double bond, definitely no geometric isomer. And then the last one, there are 2 hydrogens on the same side of a carbon, so there's definitely no geometric isomer. So that's how we decide whether something have a geometric isomer or not, very quickly, just by looking at the symmetry. Okay? If that's clear, could you please type a 1 to the Skype chat? Yeah, if that makes sense to you. Yeah, so the next question, I just want everyone do it by yourself. So the next column will have 5 different things. Yeah, can everyone type to the Skype chat how many molecules you think have geometric isomer? If you think out of those 5, there are 2 have geometric isomer, just type a 2. Yeah. 3, just type a 3. Okay. The next column. Yeah, so this should be fairly straightforward. And you can see this one, 2 chloro atom, there's definitely no. Okay. And then the last one, yeah. And then this one here, you can see on the 2 sides of the double bond is completely different. So there's definitely an E and Z isomer. Yeah, there's definitely an E and Z isomer. And then, yeah, this one here, yeah, so this is hydrogen, this is chlorine and carbon. So the 2 sides are definitely different. Okay, so yeah, you see you have a methyl chloro, you have a hydrogen, you have a chloro, you have a methyl group. So 4 groups are all different. Yeah, so 4 groups are all different. There's definitely E and Z isomer. Yeah. And this side also different, so there's also E and Z isomer. Yeah, and then the last one all different, of course, there's E and Z isomer. So there are 4 of them have E and Z isomer. Okay, 4 of them have E and Z isomer. So lots of people type the 3. Yeah, Phil, could you please tell us like which one you think it's not a geometric isomer? The last one. Okay, yeah. So Phil thinks the last one doesn't have a geometric isomer. And Geoffrey, you type the 3. Which one you think doesn't have a geometric isomer? Like when you count 3. Okay. Yeah. So just go through. Yeah, the 4th one, the 5th one, the one like Phil and Geoffrey draw there. Yeah. So the last one here. Yeah, the last one here you have CL, C, CL, C, right? That's the one Phil pointed out. So you can have the 2CL on the same side. This is cis because 2CL on the same side. Or you can have the 2CL on opposite side. Okay, or you can have the 2CL on opposite side. That would be a trans. Yeah, so the last one is definitely an E and Z isomer. Yeah, because when we say symmetry, it's on one side of the double bond. Okay, yeah, its symmetry is not on top of the double bond or on the bottom of the double bond. It's one side of the double bond. So you need to draw a line across the double bond. Only have a look at one side. Yeah. So except the first one, where you can clearly see the 2 chlorine are exactly the same, none of them, sorry, all the rest are geometric isomer, have geometric isomer. Okay. Yeah, if that's clear, could you please type a 1 to the Skype chat? So the answer is 4. Okay. Yeah. So the next one, again, I want everyone give it a go by yourself. How many do we start with? 1, 2, 3, 4. Yeah. So we start with 4 molecules. Yeah, and then think about it, whether how many do they have geometric isomer, and then type it to the Skype chat. Okay. Yeah. So we start with 4. Yeah. The first one is not a cis or trans. Oh yeah, the first one. Yeah, the first one should be a cis and trans as well. So that's not a double bond. Yeah. Yeah, thanks, Phil. Let me just get rid of this. Sorry, that's a really silly mistake. This one should be a cis and trans isomer because, yeah, so this is a hydrogen and this is a hydrogen. So the 2 hydrogen can on the same side or can on opposite side. So this is a E and Z isomer as well. Yeah, sorry, that's just a really silly mistake. Yeah. Question, Ikra. Yeah. If they're different on both sides, then it's definitely a geometric isomer. If they are the same on one side, it's definitely no geometric isomer. Yeah, no problem. So just quickly write it here. Uh, yeah, so as long as on one side 2 things are the same, then there's no geometric isomer. Yeah, so as long as there's one side 2 things are the same, there's no geometric isomer. If you want to have a geometric isomer, you need to make sure there are 2 things happening at the same time. The first one is x count equals to y. The second is a count equals to b. Okay, yeah. So if you have a structure formula satisfies x doesn't equals to y and a doesn't equals to b, so none of the side can be the same, then you can have a geometric isomer. Okay, then you can have a geometric isomer. If any side are the same, you definitely don't have a geometric isomer anymore. Okay. Yeah. Yeah. Yeah, you count them as two. Yeah, you count them as two molecules because they're different. Yeah. Mm. Yeah, it's a E and Z isomer. Oh, we're looking at the double bond, not that carbon. So you see the double bond is in the middle? We're only looking for the double bond. Yeah, so I'll just elaborate on the one Phil pointed out because that confuses me as well. Yeah, so this is one. How do we know whether this one is a geometrical isomer or not? You only look at your double bond. You only look at your double bond. So this H3 we replace it with M, so it's just a methyl group. And then this entire thing is like a dichloromethyl, we just replace this with a D. So that's just like an entire thing is called dichloromethyl. Okay, yeah. So you can see with this double bond, you can either have two hydrogen on one side, and then a dichloromethyl and another methyl. So this would be a cis isomer, or you can have one hydrogen here, one hydrogen down the bottom, and then you have a methyl, and then you can have a dichloromethyl. So this would be a trans isomer. So that's your cis and trans. That's why it's a geometric isomer. If the double bond is over here, yeah, if the double bond is in the blue position, then you definitely don't have a geometric isomer. Yeah, does that make sense? Yeah, let's just come back to this. So there's four of them. 1, 2, 3, 4. Yeah, can everyone type it to the Skype chat? Like how many geometric isomer you think there are? Yeah, so there's actually one. Okay, there's only actually one because this one, okay, 2Cl on same side. Okay, 2Cl on same side, so there's no geometric isomer. This one, 2 hydrogen on same side, definitely no geometric isomer. This one, 2 hydrogen on same side, definitely no geometric isomer. This one, you definitely have a geometric isomer. Okay, so there's only one of them. I will just quickly go through the rest together. Yeah, so you can see, for a ring, if you want to have a geometric isomer, you need at least two things around the ring. Yeah, so you need have at least two things around the ring. So one, so if both above the ring it's cis, both below the ring that's also cis, they are the same. And then it only makes a difference if one above, one below, then you can have a trans. Yeah, so you need to have two, at least two substitution group along that ring. Yeah. So now let's just come back, have a look at it. The first one is impossible to have any geometric isomer because you only have one thing pointing out. Okay? And then the second one, you can have a geometric isomer. Yeah, so the two chlorine groups can both go down, or one goes down, one goes up. So that's fine. And then this one is the same. You can have both chlorine group goes up, or one goes up, one goes down. Okay. And then this one here, there's only one substitution group, so the answer is no. Yeah, this one here, it is yes. Okay, so you can have a E and Z isomer. Okay, and then the next one is no, because you only have one substitution group. And then the last one here, yeah, it is yes. Okay, yeah, because you have two substitution groups, they can both going up or both going down. So this one you could have yeah, E and Z isomers. Yeah, E and Z isomer. Oh, sorry. Yeah, I just made a really stupid mistake. This one you can't. Yeah. This one you can't, because again it's symmetrical about the plane. So this one you can't have a geometric isomer. Yeah, I will illustrate this in a second. This one is no. And then the last one here, yeah, the last one here you can, yeah, you can, yes. You can have the two chlorine both pointing up or the two chlorine both pointing down. Yeah, so I'm just going to quickly explain this one here and this one here, like those two, why they can have geometric isomers and another one can't have geometric isomer. Okay, and then that's all. Yeah, so one of them is this. We said there's no geometric isomer, and then one of them is this. Yeah, we said this could be E and E or Z isomers. Yeah. Yeah. So let's just draw it in a 3D view. Yeah. So just imagine this methyl group is always pointing up. Yeah. So you have a chlorine group pointing up and another chlorine group going down. And then these two chlorine, like they has to, one goes up, one goes down. But yeah, but the methyl group you can choose to goes up or down. Yeah, but you can see those two, it's just mirror image of each other, right? Yeah, this image. Yeah, they're just, yeah, you just flip it and then, yeah, you just rotate it, it will just come back to there. So it's definitely, yeah, it's definitely not a geometric isomer because you don't have like cis or trans. However, this one it can be cis or trans. Yeah, however, this one it can be cis or trans because you can have a methyl group. Yeah, you can have the methyl group coming up and then the chlorine group going down. Yeah, and then similarly you can have the methyl group coming up and then the chlorine group going down. Yeah, however, for the last chlorine there, if this chlorine coming up, yeah, you can see that's a trans because one chlorine coming up, one chlorine going down, so that's a trans. And then if this chlorine going down, they both going down, so that's a cis isomer. Okay. Yeah. And you can see the reason this one doesn't have a geometric isomer, you can just kind of treat this ring as a double bond, right? It's like you have a double bond here, and then on one side of the double bond you have two groups exactly the same, right? One side of the double bond you have two groups exactly the same. That's why there's no geometric isomer.